Hey, welcome to Ones and Zeros. My name's Ben, and today we are doing another video in our FPGA Basics series. In this one, we're going to take a bit of a look at ROMs, or read-only memories, and how we go about actually creating one of those, as well as how we can actually use ROM to enable us to be able to use the 7-segment displays on our D0CV board that we have here that we've been using in a bunch of the other videos. Just first up, want to say a huge thank you to all of the people that have been watching the videos and liking and subscribing. That's really awesome. And a big thank you to our 3 Patreon members that we have now. Let's get into having a bit of a play with some stuff, and we'll get some ROMs happening. So essentially what a ROM is a place where you can actually store sections of data. So if you think about it like an array of registers, effectively, where you can have data in each one of those, and you supply the ROM with a particular address that allows you to get access to a particular section of memory. So if we draw a bit of a diagram here, we'll get, say this is our ROM, and we'll say that we have, let's go with 4 different items of data in here. Let's say that we make this 8 bits wide, and we'll have our array of 4 data. Now with a ROM, unlike a RAM, you can't write data to it, you can only read data from it, but it operates fairly similar in principle. The main difference being that with a RAM, you can actually write new data to it rather than just having a set of constant data stored in it. Now, with the ROMs that we're going to create in this episode, they require an address to be supplied. Excuse my messy writing. And in this case, with our example we're drawing here, because we've got 4 different items in our list, we would want to be supplying enough bits of an address that would allow us to access any one of those 4 items. So in this case, we'd need a 2-bit address to give us 4 separate values in the address so that we can access any one of those 4 items. So we'd have our 2 address lines coming in, and that way this one would be at address 00, 01, 10, and 11, which would allow us to access the relevant data that's in those. And then we'd have a data bus coming out, in this case because we've got 8 bits for each of our items of data. We'd have an 8-bit bus, so that if we supply a particular address, so say if we supplied 01 on our address lines, then the data that's stored in this, our second item, would actually be sent out on the data bus. So that's a basic kind of overview of how that works. Where we get into using them with 7-segment displays can be really useful, because with the 7-segment displays that we're going to be, the way we're going to be setting them up is we want them to be able to display hexadecimal values, so that each digit on the 6 displays can display a value from 0 through to F. And in so doing, we want to be able to get the respective segments lit up or turned off depending on the particular item that we want to show. So say if we had our 7 segments like so, and say if we wanted to display a 7, we know that we want those segments on to display a 7. If we wanted to display a B, then we'd want these particular segments on. We can't do it like that because that would effectively be an 8. Just erase that one. And we also can't do it. We want to make sure it's different to the 6 as well. So we'll kind of see how that works a little bit anyway. But basically, we've got our 7 segments. So if we were to create a ROM that had 7 bits worth of data stored in each of the items in the ROM, and we know that we need 16 different values, 0 through to F for hexadecimal, then we know we can supply a 4-bit address to then figure out which segments we need to be able to display. So that way a ROM can actually be used as a decoder to decode our 4-bit value to what we actually need to have for the display to work correctly. Hope that's not too confusing. So let's get into a bit of an example with that. We're going to have a look at actually creating a ROM first, and we'll sort of see how that works in practice, not just with the diagram. And then once we've had a bit of a look at that, we will go through and actually get the 7-segment driver sorted out so that we can display data on each of the 7-segment displays. And by displaying hex values, we can actually work it, for example, so that we can have groups of 2 7-segment displays, so that each group of 2 can display an entire 8-bit byte, which then comes in really handy because we can actually start to use the 7-segment displays to help us with debugging or displaying data or things like that. So let's jump over to this one. We'll get a project created so that we can start having a look at this. We want a new project. Let's just pop this on the desktop. And I will put the code from this episode up on GitHub in our FPGA basics repository as well. So if you want to try it out, then you can feel free to do that. We'll call it ROM 7seg. And much like I've done previously, I'll just pop up the Verilog files rather than the entire project. So empty project, we want our D0CV. Don't worry about any of that stuff. Let it create the project. So in this episode and some of the following episodes, we're going to start to get into some of the more fun stuff that I enjoy a little bit more. This episode we're doing now because the 7-segment displays will come in handy for a bunch of the stuff that we're going to be doing in following episodes. So let's get our file sorted out. So we've got our inputs and outputs and our top level module. Get that file saved. Actually, we'll delete that one first because we're not going to want that one there. Just save that one like so. Get that one out of our project and set that as our top level entity. And we are good to go. All right, so essentially to be able to create a ROM, let's have a look at that first and we'll sort of see how that works. Let's save that one. We're going to create a new file, which we're going to be popping our 7-segment display stuff in. So let's get that created first up. Pop. Don't want that. Just want a header for that one. nice if this would actually copy correctly. There we go. And we'll call that qa7seg.v. It's automatically added it to our project. Let's create a module for a ROM. And in this case, we might do it like the example and just have something simple in there initially. Now we can either create it with a sort of set address width and data width for a specific thing. So say when we go to do the 7-segment displays, or if we wanted something that we could kind of reuse and have a different amount of data that we want stored in there and different data widths, then we could go through and create a module that has parameters, which we might do for this first example before we actually do the... Might even just call this QA ROM module at the moment, and we'll see how we can do that. So let's create a couple of parameters with some default values. We'll have a data width of 8 and an address width of 4. So that'll give us 16 items. Each of those items is going to be 8 bits wide. We're going to want some inputs and outputs. In this case, our inputs will be our address. And we can use our parameters here to say it'll be address width -1 down to 0. So that's going to be 7 down to 0. 4 down to 0, sorry, for address width, which gives us 4 bits worth of address. And then we can do something similar with our data width, which gives us 7 down to 0 for our data, so that we have 8 bits worth of data. And we'll pop an end module in there. And we're going to create an array of registers effectively. So go reg data width -1 down to 0. So we get 7 down to 0 for that. We're going to call this one ROM. And we're going to tell it that it's going to be an array. So we're going to do another square brackets, and it's going to be 2 to the power of address width -1. Might even just pop that in some brackets. So doing the 2 stars is the equivalent of doing a power. So this is 2 to the power of an address width. Actually, we want a 2 to the power of address width and then the -1. So we don't want the brackets there. So it's going to be 2 to the power of 4. Which is going to give us our 16. And then -1, which is 15. So 15 down to 1 gives us 16 items in total. So that's how we go about creating that. So we're telling it the width of the registers and then how many of them we actually want in the array. So I think that's the first time we've looked at arrays in any of these videos. Now, because we're dealing with a ROM, we're going to want to be able to have data in the ROM that we can access. So in order to do that, we're going to use an initial statement. And we're going to use readmemb. There's readmemh and readmemb, which allow us to read either binary values or hexadecimal values from a file, which I'll explain a little bit more. I'm just going to call this qa_testmem.rom. So we basically specify the file name that has the data stored in it that we want in the ROM and where we're putting it. which will give it the name of our array of registers here. And then we also want to assign our data output to the particular element in our ROM that our address is pointing to. So similar to the way that you might access an array item in another programming language, we do the same thing in Verilog, where it's the name followed by square brackets with the index in it, just like so. So that way, if we supply a particular address, it's going to output on data the item that's in that address. Now let's create this file so that we've actually got some data in there that we can test with. I find the easiest way to do this is just tell it to create a new text file. Now with this, as I mentioned, we've got readmem-B or readmem-H, so we could change that to H if we wanted to use hexadecimal. In fact, we might do it with hexadecimal for this one and then use readmem-B for when we're doing the actual ROM for the 7-segment displays. So in here, what we can do is basically just do a list of the actual data that we want stored in those particular addresses. And we know we need 16 items, so let's just pop some random stuff in there. So 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and 16, let's go with 66. So all hexadecimal values because we're using readmem-H, otherwise we'd just be using zeros and ones to represent the bits, and because we're going 8 bits wide and each hexadecimal value represents 4 bits, we do 2 values for each of the items in the array, like so. And what did we want to call it? QA_test.mem. So we'll save that. Let's call it test.mem. And even though text files are selected, it still should save it with the correct extension, which it has, which means that that data is going to get loaded into our ROM for us. Now, in order to actually try this out and see how that ROM works, what we're going to do is wire up 4 of our switches to the 4 address lines, and then we'll wire up our 8 data lines to our LEDs so that we can actually get those to display the data that is sitting in whatever address we're supplying. So let's create a couple of wires for our various bits of stuff that we need. So we're going to need a 4-bit wire for our address. Call it address bus, and that one we will hook up to switch 3 to 0. Also create a wire that is 8 bits wide for our data bus, and we're not going to assign anything to that because that's going to be hooked up to our LEDs. Now we call this one QA ROM module, so we can just go QA ROM module, QA ROM, and then we can basically just keep the default parameters if we like, which we'll do for the moment, or we could actually override those parameters as well if we wanted to. And then let's assign LED R 7 down to 0 from our data bus, like so. Make sure I haven't missed anything there. Let's try compiling that one and see how we go. All right, it's completed analysis and synthesis, so no bugs in our Verilog. Now, the other thing that we can do with ROMs and RAMs as well is we can actually specify whether we want them to be created using logic, so as in our logic elements or adaptive logic modules in the case of the Cyclone 5, or if we actually want to use the dedicated RAM blocks rather than the logic blocks in order to make that one work. Or we can just let the system figure it out for itself, depending on what it feels is going to be the best option. Now, we're only using 5 ALMs and 0 bits of memory, which makes me think it hasn't quite worked correctly. So let's check our RTL viewer. No, it has definitely created a ROM for us. So we can see the 4 bits worth of address coming into our ROM, and that's going out to our LEDs on our data bus. So that actually looks correct. Not using much in the way of resources to be able to make that happen though. So it may just be that it's actually really efficiently done that. Let's have a look if we get this programmed onto our device, and we'll double check and see if that works. So pop that on there, jump over to our board, and we can see at the moment we've got all of the LEDs lit up, which, given the particular data that we put into our file, we put FF into the first item. We're currently supplying it an address of all zeros, which would point to that first item, which then gives us all of the LEDs lit up. If we go to the next one, we should see our rightmost LED turn off, which gives us the value of FE. That'll give us AB, which is the third item that we've got stored there, so all of that seems to match up. It's a bit hard to see with the light shining on the LEDs. Let's see if we can fix that. That's a bit better. Doesn't help that we've got the 7 segment displays all lit up at the moment. So we can supply different addresses via our switches, and we're able to retrieve the specific bits of data that are being stored at those addresses. So our ROM actually works correctly, which is great. Now let's jump back to our screen and into this one. And as I mentioned, we can actually force it to use either logic or to use one of the RAM blocks to be able to set up the ROM in this case. If we have a look at our chip planner at the moment, we'll see that it's actually using adaptive logic modules to make this work. Not much in that one. This one's also being used. There's a bit more usage going on in that one. Now, the other handy thing I'll just point out in here as well is your scroll wheel will normally scroll up and down. You can hold down Shift and it'll scroll left and right, or you can hold down Control and zoom in and out. So that makes it quite useful. Now, we can see the little white boxes on the right-hand side of these adaptive logic modules, which are actually our registers. And these bigger blocks on the left are our lookup tables or combinational logic, which shows that it's managed to figure out how to simulate that ROM behavior simply through combinational logic. It's not using registers to do that or RAM blocks at all, which is really kind of cool. I'm always slightly fascinated by how it manages to figure out how to fit the design onto the FPGA. If we wanted it to actually do it so that it was using one of the RAM blocks, we can make use of RAM style, and the particular blocks that we've got on this device are M10K. So if we put that before our register array definition, then that will tell it that we want it to actually use one or more of the RAM blocks to make that happen. So if we compile that now, we should see that if it compiles correctly, we should actually see memory block usage rather than it using combinational logic as it did previously. And there may be certain situations where you'd prefer it to do one over the other. Much as we can do this and force it to use a RAM block, we can also use that same RAM style and put logic in it instead of M10K in order to force it to do that in logic rather than doing it in RAM. Or as we did it at the start, you can just not specify and it'll figure out what it thinks is the best approach. So that's compiling okay. Doesn't seem to be any bugs there, which is awesome. Beta stage is complete. Does seem to have ignored what we asked it to do though, which is a little bit curious. Let's have a look through here. So this is where it starts to elaborate that one. Okay, so it hasn't gone with an actual RAM block due to the fact that there's no clock being supplied to it for that ROM, which we're not going to worry about in this episode, but just bear in mind that you do have the option. We will look at RAM and using clocks with RAMs and things like that in a later episode. But just be aware you do have the option with a RAM or a ROM, depending on how you set it up, to specify whether it's going to use logic elements, which we could do that way, or whether it's going to use memory blocks, in this case M10K blocks. If I was using one of the Cyclone 4 devices, then they would be M9K blocks. And you can find the information on that particular item in synthesis attributes, where it does specify how that works as well. So if you need to refer back to that, it does tell you what the legal values are there that you can supply, and gives you a little bit of an explanation as well. So just wanted to kind of point that out. So that's how a ROM works. Let's go through and have a look at how the parameters could be used. Let's just pop that over there. So in our instantiation of the module here, we can actually go in and specify our parameters. So we've got data width and address width. So we could, for example, say if we wanted to double both of those, we could go data width equals 16 and address width equals 8. And it would then override the default values that we've put in here, these guys, in order for that to take effect. Now I think we may also need to put the parameter keyword in there. Let's just double check if that compiles so that I make sure I'm giving you guys the correct information there. And this can be handy because you can create one module that has a particular purpose, and then you may want to use it with different data widths and things like that. Say if you had a arithmetic logic unit, just pop the parameter keyword in there. I'm pretty sure that's what it is wanting. Let's try that. So say if we had an arithmetic logic unit that we've created for a processor, and say if we wanted to be able to reuse that in a couple of different parts of our design and have one that's 16 bits wide and one that's 32 bits wide, you could use the same module and just specify the different data widths for the parameters. Curious. Don't very often use, let's just get that off there. Don't very often use these. Let's just double check. That one. It should actually be correct. Why is that not? Okay, so we don't need the parameter keyword in there. Not enough coffee this evening. See what the error is that we get with that. It's always fun when I test things before doing a video and then completely forget when I actually go to do the video. Let's just jump over there. Haven't misspelt those at all. That is a curious one. I wonder if it just doesn't like those all being together. I don't think that's it, but let's have a look. If not, we will continue on regardless. It's just got me slightly curious now. No, still has an issue with that. We'll come back to that in a future episode anyway, but let's get rid of that for the moment and let's create the stuff that we need for our 7-segment displays. So we're going to create a module that we can use for each digit in the display. So we'll have a 4-bit address bus and a 7-bit data bus because we've got 7 segments. On this board, the decimal point for each of the digits is not hooked up, just the 7 digits that are used for the number. So we'll just go with a 7-bit data width. I'm going to delete our test.mem file from the project there. And let's delete, actually we might just modify this module to suit what we're looking for. I'm going to get rid of our parameters. Like so, and we're just going to hard code these guys. So that'll be 3 to 0 to give us 4 bits of address and 6 to 0 to give us 7 bits of data. Let's get rid of that one. We're going to let it figure out the best way to make that work. And that will be 3 to 0. No, it'll be 6 to 0 for our data width. And this will be 2 to the power of 4 minus 1 for our address. I'm going to call the file that we're going to be reading from qa7seg.mem. Because we're going with 7 bits wide rather than 8, we're going to do the file in binary rather than hex like we did before, but the rest of that will be the same. And we'll pop some comments in here so it makes a bit more sense when we pop the code up on GitHub. Let's make that look a little bit neater. Excellent. So that's our ROM module. We're going to need our file containing the data that's going to be going into that. So much like we did before, we're just going to create a text file. This one, We're going to go with one that I've prepared earlier that has the data for the particular segments. So we can see for each of these it's got 7 bits in binary, and you can also pop comments in the file just using the double slashes as we've got here as well. So that way you can help it make a little bit more sense. Like so. So that's our ROM, and then we're going to create a module that handles all 6 of our 7 segment displays in one go, so that we can basically hand it 3 bytes worth of data and it will display those in hex on the displays. So I'm going to call that QA 7seg module. Have some inputs. We're going to have 3 inputs to allow us to enable or disable each byte of the display, so each group of 2 digits, and that way we can do that independently. We're going to have our data coming in, which is going to be 24 bits wide, so that we can feed in 3 bytes worth of data to be displayed. And doing it as a 24-bit bus allows us to do, we could use it as being able to display 24 bits worth of data in one go, or a group of a single byte with a 8-bit value and a 16-bit value, so using 2 segments and 2 digits and 4 digits respectively, or we could have it so that it's 3 separate bytes. And we're going to have 42 outputs because we've got 6 digits with 7 segments each. And we could break this up in different ways if we wanted to, but this keeps it fairly simple. Rather than having to have a bunch of inputs and outputs, we've kind of just got the 3. So I'm going to do our first digit, which will be our rightmost digit. Create a 7-bit wide wire there, and then we're going to create an instance of our ROM module. Call that QA7seg 0. That'll be getting data from the first 4 bits of the data coming in. So bits 3 to 0, and the data coming out of that one will be going to our seg0 wire here. And then for the other digits, we can just copy and paste that, change that to segment 1. And again, there's probably other ways we could do this as well, but this sort of keeps it fairly simple. So this will be taking bits 7 down to 4, so the next 4 bits of our data coming in and outputting on segment 1. And same for the other ones respectively. That'll be 11 to 8 for our next 4 bits worth of data. And outputting on seg2, segment 3. That will be 15 to 12. Number 4, which will be 19 through to 16. Segment 4, and make sure we fix that one up, or we're going to have a bug. Number 5, which takes us to 23 down to 20, and outputting on the segment 5 wire. So that's our 6 ROMs, and then we'll sort out our output. So we're going to create a 14-bit wide wire to handle 2 digits of 7 segments each. Go byte 0 out equals enable in 0. So enable in bit 0 will control our first 2 digits, 1 will control our next 2, and 2 will control our final 2 digits of the display. And in here, if enable is on, then we're going to be outputting seg1 and seg0, so the output wires for those guys, which will be combined together into 2 groups of 7 or 14, which matches our wire here. And if enable is turned off, then we are going to output all zeros. Now we can just copy and paste this guy a couple of times as well. Getting our respective enables for that one. So this will be segment 3 and segment 2, and segment 5 and segment 4, which gives us all of our outputs. Now, as we've mentioned in previous episodes as well, our 7-segment displays require an inverted signal. So if we supply a binary 1 to a particular digit, it will turn off. If we supply a binary 0 to a particular digit, it will turn on. So we're actually going to invert the data going out as we send it to our segment output, which we should actually specify as an output. That might help. Definitely not enough coffee this evening. Like so. So invert that with the little tilde symbol, and then we can just combine byte 2 out, byte 1 out, and byte 0 out into one 42-bit wide bus. So got our enable and our data coming in. Our data is being sent in chunks of 4 bits to our 6 ROMs, 1 for each digit. We're then combining those digits into groups of 2 so that each group of 2 displays a byte, has its own enable on our enable in signal, and then combine together to provide our segments out. So that's how that one works. And then let's jump to our top level module and create something so that we can test it. So we might create 3 8-bit registers so that we can store data to display on each of the groups of 2 digits. So byte 0, byte 1, and byte 2. We're also going to set up a wire that is byte input, which is taking data from 8 of our switches so that we can actually use those to store data in each of the respective bytes. Like so. We're going to have a clock signal, which we're going to take from push button 0, and it'll, because they're active high signals, we'll invert that one. And then we're going to have the other 3 keys specifying which byte we're actually loading. So key 1 will allow us to load byte 0, key 2 will allow us to load byte 1, and key 3 will allow us to load byte number 2. And then, as we don't have 3 more switches left over, we might just use a single switch to allow us to turn the digits on or off all in one go. So we'll call that seg on off, and we'll get that from switch number 9. So we still have using 8 switches for the data input, 1 switch to turn the displays on and off, and we also have a spare if we wanted to use that for something as well. We're going to do an asynchronous reset on this one, so on the negative edge of reset and or the positive edge of clock. And I'll have a video coming out shortly talking about the difference between synchronous and asynchronous resets. So if we're holding down the reset key, then we want to clear the data that's in each of our byte registers. Again, using the less than symbol and the equals because we're doing a transfer on a clock pulse, or on the reset pulse in this case. And then if we're not resetting and we're clocking it while holding down the load byte 0 key, then we will store the data that is on our byte input from our switches into byte 0 and copy and paste that for our other 2 bytes. So load byte 1 will store into byte 1 and load byte 2 will store into byte 2. So that allows us to store 3 bytes worth of data independently of each other. And let's get just put byte data for that section. So that's what that's handling, and this is actually handling our 7-segment displays. So we're going to need to supply our inputs to the module that we created. So we're going to need segment enable, and probably need a way to write this, but we're just going to put segment on off 3 times so that all 3 of those segment or byte enable signals are getting the same value. Need our data going into our 7-segment module, which is our 3 bytes. So we'll just group those together to give us our 24 bits there. And then we're going to have our 41-bit wide bus coming out, which we'll call segment output. Create a instance of that module. Need to supply it with segment enable, segment data, and segment output. And then we can connect everything up to our respective displays. So bits 6 through to 0 will go to our first display. (13) through to 7 go to our next one. 20 to 14. 27 to 21. 34 through to 28. And lastly, 41 to 35. And we might also display on our LEDs the actual data that we've got that we're going to input from our switches, like so. So we've got the stuff to be able to store our 3 bytes independently so that we can display something on our displays. We've got our 7-segment display module, and then also displaying our input data on our normal LEDs, like so. Let's compile that and see if we get any bugs. In the next video, we're going to be making use of the 7-segment displays. We're going to start taking a look at shift registers and being able to use a combination of the 7-segment displays. Save that in output files. That's clever. Let's go file, save as, and pop it in there instead. Delete that one. Helps if we save the file into the right spot. That should compile. So as I was saying, the next video we're going to be looking at shift registers, which are going to be making use of the 7-segment displays. And they're really handy because they allow us to convert data between serial and parallel, or vice versa. And quite simple to sort of set up, and can be handy if you're, say, doing something like a SPI peripheral or something like that, where you need to take data that you've got stored as, say, a byte and then send it out the peripheral in with each bit in a serial transfer. So we'll have a bit of a look at that one in the next video. So no more bugs, it's up to the fitter stage. Now I'll also put that 7-segment memory file in the, along with the Verilog files in GitHub as well. So most 7-segment displays have the digits in the same spots, and depending on how, like if you've got a different development board, depending on how it's wired up, you may need to modify things slightly, but I'll pop it there anyway, just so that you've got that as a bit of an example to work from if you'd like. And we are all done. Let's get that programmed. Pop that across to our device. And we are all programmed. So we've got our displays turned off at the moment. So this switch on the left-hand side should allow us to switch those on or off. And our byte 0, byte 1, and byte 2 all have 0 values stored in them at the moment. Let's go through and actually test to make sure that we're getting the correct display for all of our 16 digits, so 0 through to F. So let's store a 1 in the first one and a 2 in the next one. Press this key to store into byte 0 and clock it. So we've got 1, 2. Let's go 3 and 4 for the next one. 3 and 4 work correctly. Go with 5 and 6. They work fine. 7 and 8. Pop that into byte 0 again, so 7 and 8. Go with 9 and A should be that one. 9 and A. That should be B, and then C. B and C. Then we want D and E, which will pop into byte 0 again, so D and E, and then we've got F. So our F's work, our zeros work. Oops. There we go. We can do all zeros for that one. And then we can go through and just store values in each of our bytes individually, and then it's going to display the respective things on our 7-segment display. So if we wanted 0F in byte 0, that's 0F. We wanted 21 in hex in our next byte. And then say we wanted 88.8 in our third one, we get 88. So we can see all of those particular values are working correctly. The various values display correctly on the 7-segment displays, and our ROMs are all working the way we want them to. So that's kind of the approach I take getting those set up. There's certainly a few things with the Verilog that could have been done to make it potentially a little bit more efficient and possibly even look a bit neater. But during these videos, I find breaking it up a little bit might help it to be a little bit more understandable if you're just starting to get into Verilog. I'm certainly not an absolute expert at FPGAs. I have done a decent bit of development with them, but primarily as a hobby. So there's probably ways to make that sort of stuff happen that are better than what I can do. But as you can see, that's one approach that works quite well with making that happen. So I hope you found that interesting. That's how ROMs work, and how we can use those to not only store data, say instructions that we want to execute on a CPU, but so that we can actually use them as a decoder. And if we have a look at our RTL viewer, we can see the logic to be able to go through and store the 3 separate bytes that are then being used as the data we're displaying on our 7-segment displays. You can see the 6 ROMs that are being used there, and then all of these guys are the inverters to flip each bit from active high to active low, so that they trigger the 7 segments of each digit correctly. Can hardly talk at the moment, definitely need more coffee. So that's how that kind of works. If we have a look at our compilation report, we can see it has only used 25 adaptive logic modules to make that work. 24 registers, which are the registers that are being used to store the 3 8-bit bytes, so 8 registers each. So still fairly light on resource usage for our Cyclone 5 chip. So thank you for watching. Hope that is something that you might find helpful. Like I said, we'll pop the Verilog files and the .mem file up on our FPGA basics repository. I'll pop a link to that one in the video description. If you found that one interesting, would love it if you gave us a like. If you're not subscribed, it'd be awesome if you subscribe to the channel. There'll be plenty more cool stuff to come. Big thank you to our 3 patrons of the channel. It's awesome that those guys are helping to support the channel so that we can continue to pump out interesting content. And thank you so much for watching.